said, hey, you, let's do some diffie-Q. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some diffie-Qs. In this video, we'll look at solving ordinary differential equations with the Laplace transform. We looked at some properties of Laplace. We've also looked at its inverse. Now we'll apply the Laplace cycle in order to solve a differential equation straight away. Let's start with something that we'll absolutely need because we're working with differential equations. We'll need to know the Laplace transform of a derivative. Here we have the Laplace transform of a derivative. Namely, if we have the nth derivative of y, the Laplace transform of it is exactly this expression here. And there are a few things to note. First, we have the presence of these s's. That starts at s to the n. Notice n is the same as this n here. So the nth derivative, or nth order, ends up being the degree here, s to the n. And this s to the n then descends to s to the n minus 1, and so on and so forth, till we get down to s, and then eventually what would be s to the 0. So we have s to the n minus 1. We keep decreasing the degree until we get to s to the 1, and finally s to the 0, which we can just write as 1. One component of this is then these s's. Notice also right away that the sign is positive to begin with, and then thereafter is always negative. All of the terms after the first have a negative sign. The final component to notice is that we have this increasing order of derivative. And by that I mean if you think of y of 0 as being the 0th derivative, the next one would be y to the first, the next one would be the first derivative of y, then the second derivative of y, and so on up till we get to the n minus 2 derivative, up to the n minus 1 derivative. Notice we don't quite get to the nth derivative. Part of that reason is we also start with something that you can consider the negative first derivative. The Laplace transform is defined as being an integral, and integration is, of course, the inverse of differentiation. So it's like differentiating backwards. So here we have the 0th derivative going backwards would give us the n minus first derivative, the integral or antiderivative in some sense. Going forward gives us the first derivative, and so on up till we get to the n minus second and minus first. So notice the degrees are decreasing with the s's, and the order is increasing with the derivative, from the negative first up to the n minus. Beyond that, notice also that we need to know some initial value information. We need to know what is y of 0, what is y prime of 0, etc., etc. We need to know each one of these pieces of information. And note that if it's an nth order, we'll need n, because it starts at 0, we'll need n initial value data point. Let's review the Laplace cycle. We're going to start with a differential equation. We're going to apply the Laplace transform to end up with this expression. Now here is where we're going to use what we just saw. We're going to take the Laplace transform of a linear differential operator. In particular, we're going to be taking the Laplace transform of some derivatives. That will give us an equality with the Laplace transform of whatever the function f is. Over here, we'll be doing some algebraic manipulation while we're in the S space. And then from the S space, once we have arranged it as the Laplace transform of just x itself, which is what we're trying to find the solution that is just x. If that's equal to the Laplace transform of some function g of t, we know what g of t should be. By applying the inverse Laplace transform, we get to the expression after having peeled away the Laplace transforms to x is equal to the function g of t. Now we've found that x, g of t, is the solution to this. It's in some sense a miracle that we can pass to a completely different space, do some work there, move back, and all of a sudden we're exactly what we wanted to have in the first place. It's really a cool process. We're lucky to have it. Let's see how it actually works. Suppose we have this initial value problem. On the left-hand side, we have a linear constant coefficient differential equation. It doesn't have to be homogeneous, but it happens to be. We also have 2 points of initial value information. Since it's a second order differential equation, we need to have 2 points of initial value information. We do, so we're good to go. Now the first thing, we'll simply take the Laplace transform of both sides of the differential equation. I've shifted it here to the right because there's going to be a lot of work that appears on the left. Now, of course, the Laplace transform of 0 is 0. And we can use the linearity property of the Laplace transform because remember, the Laplace transform and the inverse Laplace transform are both linear, which allows us to break it up across addition and pull out constants. Here, I've done that. Now, we're going to use what we just saw at the beginning of the video. We're going to take the Laplace transform of derivative. We do so. Now, taking the Laplace transform of x, it's just itself. This is the thing we're trying to solve for. But we take the Laplace transform of the first derivative. That gives us s times the Laplace transform of x minus x of 0. Now, notice we're still multiplying the 2 by that. So that stays. Same thing with the 3. We're going to multiply 3 by this substituted expression. And taking the Laplace transform of x double prime, we use the formula we saw at the beginning of the video to make a substitution here. Once we've done the substitution, we can now rely on our initial value data. We know that x prime of 0 is 0. We know that x of 0 is 1. Those will be substituted appropriately into these formulas. Doing so, we now have this expression, or this equation, and notice we've just done a recoloring, which if we substitute, gives us the following. X of 0 is 1, and x prime of 0 is 0. So here, we're left with just negative x, and so on. Now what we'll do is we'll combine like terms. All the terms that have a Laplace transform of x, we'll combine those. All the terms that do not, we'll combine those. So here we have Laplace of x times the 3 terms that had Laplace transform of x as a factor. Besides that, there were 3 terms that did not, being careful to make sure we distribute properly. There were 2 terms that did not. We leave those there. We now solve for the expression of Laplace of x is equal to 3s plus 2 over 3s squared plus 2s plus 1. Now, let's focus on the fact that we have the Laplace transform of x is equal to this expression. Then if we take the inverse Laplace transform of both sides, we'll have a cancellation on the left-hand side, and that leaves us with x of t is simply the inverse Laplace transform of this expression. Now what we've done is we've set ourselves up so that if we can find the inverse Laplace transform of this expression, then we will know what the solution is. We wanted to find the solution x of t is equal to some expression of t, and now we're really close. It's just left to find the inverse Laplace transform of this expression. Now, in order to get this ready to actually apply the inverse Laplace transform, we'll have to do quite a bit of algebraic manipulation. So remember when I said in the Laplace cycle that while we are in the S space, we'll need to do some algebraic manipulation? That's what I was talking about there, and that's what we'll be doing here. We'll algebraically manipulate to set this up so that we can easily compute the inverse Laplace transform. Supposing that we have our expression and not worrying about the Laplace transform at the moment, we'll just algebraically manipulate it. First thing we'll do is we'll factor out a 3 from the denominator. Then we'll factor out a 3 from the numerator. Doing so, we get 3 over 3 that cancels. Now what we've done is completed the square. We've taken 1/3 and we've partitioned it. That's the word I was looking for in the last video. We partitioned it into 1/9 plus 2/9. Add that up, that's obviously 3/9, which is 1/3. The reason we've partitioned it like so is if you take 1/2 of this coefficient in front of the linear term, which is 1/3, you square that, you get 1/9. That is the number that you want to be here. So we effectively peeled 1/9 off of 1/3. Taking 1/9 away from 1/3 leaves us with 2/9. Now, this magenta expression, we're going to factor. We've chosen exactly that plus 1/9 so that when we factor it, what we get is s plus 1/3 squared. This is called, again, completing the square. You saw it a long time ago in algebra class. And it's an easy thing to forget because it pops up here and there. Sometimes you use it a lot for whatever you're working on. Sometimes you don't even think about it at all. But this again is called completing the square. Now from there, we'll further partition an element in the numerator. Namely, we'll partition 2/3 into 1/3 plus 1/3. The reason we do so is if we notice down here in either one of these lines, we have s plus 1/3 squared, we have s plus 1/3 squared. That means if we want to have s plus 1/3 up top. When we partition this a little more, I think it'll make more sense. Notice also that we took 2/9, and since whenever we have something like s squared plus blah, 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 if it's plus a positive number, we want to write that number as something squared. Square root of 2/9 is root 2 over 3. So 2/9 can be written as root 2 over 3 squared. Simply do the squaring. Square root of 2 squared is 2. 3 squared is 9. We get 2 over 3. Now let's partition a little more. One term that we'll get is simply s plus 1/3 over this expression. But then we're also going to have another term, which is the 1/3 over this expression. Now, this should be hopefully seeming a little familiar. If you think about having an s instead of s plus 1/3 here, and an s instead of s plus 1/3 here. If you had s over s squared plus something squared, the inverse Laplace transform of that is cosine of the appropriate thing, namely cosine of root 2 over 3 times t. Here we have s plus 1/3, which means there's a shift. We've seen this in previous problems and videos. There's a shift here, but otherwise it really is just cosine. Alternatively, this is very close to sine, but there is a shift again, and we need to make sure that in the numerator we have this. So again, cosine shifted by negative 1/3, sine shifted by negative 1/3. And now we've multiplied and divided by root 2 over 3, because that is the number here. And now you'll notice that this is in exactly the form we want for sine, namely sine shifted by negative 1/3. Let's now summarize what we have so far. Going back to our previous work, we have that x of t is equal to the inverse Laplace transform of this expression. We then did some algebraic manipulation while staying in the S space. That brought us to this. Now we'll use the linearity of the inverse Laplace transform. We separate it across addition, and then we factor out any constants, which gave us the root 2 over 2. Now the inverse Laplace transform of these are going to be respectively cosine and sine, but with the appropriate shifting. So here we have cosine in the first case, sine in the second case, but we have shifted appropriately by e to the negative 1/3 t. And this can of course be found in your Laplace transform table, or any Laplace transform table. And this of course can be found in most Laplace transform tables. Now let's talk about the Heaviside function. Suppose you have a function such as cosine of t. A graph of that might look something like this. If you then also have a function, let's say the Heaviside function, where we shift it by 4, so that the point at which it jumps up from 0 to 1 is when t is equal to 4. Now if we were to multiply the Heaviside function times cosine, every place that the Heaviside function is 0, that would make the Heaviside function times cosine equal to 0, because you'd have whatever cosine is times 0. So it would flatten it, or cause it to vanish essentially everywhere up until you hit 4. After that, you would be multiplying the cosine function times 1, so then that amounts to just having the cosine function. So taking the product, what we get is something that is 0 whenever the Heaviside function is 0. After the Heaviside function becomes 1, multiplying cosine by that heavy function is multiplying cosine by 1, which then gives you just the regular cosine curve. Now keep this in mind as we now try to compute the Laplace transform of something like a Heaviside times a function. Here we've written the Heaviside function at a. It's 0 until you get up to a, and then starting at a, you jump up to 1 and you're 1 thereafter. Graphically, that looks like this. We're 0 until we hit a, and then from a we jump up to 1, and then we stay at 1 thereafter. Now if we want to take the Laplace transform of, let's say, a Heaviside function times a function that is already shifted by a, let's see what that looks like. By the definition of the Laplace transform, what we have is exactly this expression, this function, times e to the negative st, and we integrate that with respect to t from 0 out to infinity. Now, how Heaviside function works, now what we want to do from here is try to write all of these terms, all of these factors in terms of t minus a. We have t minus a here, we have t minus a here. We would also like to have t minus a here. The reason being is, if we did, we would be able to rewrite this integral and solve nicely. We can do some algebraic manipulation so that what we get is negative s times t minus a. So note that we've replaced t with t minus a, but in order to compensate for that, we'll also need to multiply by e to the negative sa. If you're not convinced that this expression in the white is equal to the product of this expression in red and green, you can try using law of exponents and do the computation to see in fact they are the same. Now, we are integrating with respect to t. Since we're integrating with respect to t, and this has nothing to do with t, but yet it's a factor, we're multiplying it by this whole expression, we can factor that e to the negative sa out. Again, because there is no instance of t appearing there, and it's a factor, so we can factor it out. Now, that leaves us with a expression that is written completely in terms of the variable t minus a. Since the Heaviside function is 0 up until we hit a, we now have that really this is the same integral here as this integral here. This being 0 means the integral won't have anything to compute up until we hit a. Therefore, we change the initial starting value to a, because going from 0 to a, there's nothing to compute, it's all 0 because of this. That's why we went from this here, this integral. It's directly responsible. Now, starting at a and also shifting by a really means we could have instead have started at 0 and not shifted any of these functions, giving us this. So notice we've unshifted, if you will, and we've changed back to a starting value of 0. This is 0, this is like t minus 0, this is like s times. Then finally, this is exactly the expression. Actually, I note here that I'm missing a t, but I'll correct that momentarily. But as long as we have a t here, this expression is exactly the Laplace transform of f of t. And again, I was missing a t here. So we have e to the negative sa times the Laplace transform of f of t. Notice f of t, period, is different than f of t minus a. So we showed that the Laplace transform of this shift of ut minus a times ft minus a, that's going to be equal to this here. So if you ever have a Laplace transform like this in the s space, and it's multiplied by e to the negative sa, you'll find that the inverse Laplace transform is simply this: the function shifted by a and the Heaviside function shifted by a. Now let's use this to do a computation. Here we have an initial value problem, and we want to solve it using what we've learned so far. Notice we're going to end up taking the Laplace transform of just Heaviside function. We'll start by applying the Laplace transform to both sides. We can use the linearity of the Laplace transform to separate across addition and subtraction, like so. Now, making the appropriate replacements, we'll get that the Laplace transform of ut minus 1 is this, using the Laplace table. Using the Laplace table again, we get that the Laplace transform of ut minus 5 is this. Subtraction remains. Using the definition of the Laplace transform of a derivative, we'll make the substitution here. We know that x of 0, 0, x prime of 0, 0, that means these terms will disappear. We finally solve for the Laplace transform of x, and we get this expression. Now there's a little more to do because we want to take this and use partial fraction decomposition to try to write this as a sum, which will then be hopefully easier to compute the inverse Laplace transform of. Starting with our partial fraction decomposition, we have that 1 over s times s squared plus 1 is equal to a over s plus bs plus c over s squared plus 1. Multiplying appropriately, we end up with this expression. Now we'll start doing some substitution. Now we'll collect like terms. Here we've now arranged it so that we can generate new equations. We'll first start by setting the coefficients of the s squared terms equal to one another. The number of s squareds on the left-hand side should be equal to the number of s squareds on the right-hand side. That gives us our first equation. The number of s terms on the left-hand side should be equal to the number of c terms on the right-hand side. That gives us another equation. And then finally, the last equation, where we just equate all the constants with no s or s squared, gives us this. Right away, we have that c is 0, a is 1, and that allows us to say that b is equal to negative. This means that we have the following equality. 1 over s times s squared plus 1 is equal to 1 over s minus s over s squared plus 1. This is good because individually each of these terms we can find the inverse Laplace transform of. Now we started trying to find the solution of this initial value problem. Part of our work led us to this expression. From there, we showed that by partial fraction decomposition, the 1 over s times s squared plus 1 could be written as this expression. We can then use just simple distribution of multiplication to write it like so. Then the linearity of inverse Laplace transform allows us to write this. Now we will know exactly what x is so long as we can compute each of these inverse Laplace transform. Doing so, using our Laplace transform table, we end up with ut minus 1 and etc., etc. This can be algebraically simplified to something like this. I hope you found this video useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.